Now it's my pleasure to invite Dr. Alex Bright. Dr. Alex Bright is TEM specialist in the Asia Pacific Material Science Electron Microscopy team of Thermo Fisher Scientific. Originally from Bristol in UK, Alex holds a master's degree in material science and a PhD in electron microscopy from Cambridge University. He worked in semiconductor devices yield analysis at Micron Technology Japan before joining Thermo Fisher Scientific in 2005. Since then, he has worked on a variety of instruments, including wafer dual beam and automated measurement tools, mainly in TEM. He is currently based in Tokyo. Dr. Alex will talk on advanced aberration-corrected TEM technology and application for semiconductor device analysis. With that, ladies and gentlemen, I hand this over to Dr. Alex. Over to you, Dr. Alex.
Thank you very much. So I'm very happy to be here. My name is Alex Bright from Thermo Fisher Scientific, and I'm going to talk today a bit about TEM technology and applications for semiconductor device analysis, including failure analysis, and with a bit of focus in particular on aberration-corrected instruments. So first of all, just an introduction. So why do we do STEM? In particular, we use STEM imaging because it can give us a lot of really important information at high spatial resolution from our samples. So this means very high contrast imaging, a lot of information about crystal structure from diffraction patterns, and also chemical composition information from EDS maps. And in many cases, this is the only way to effectively image, measure, or map the structure of devices, which have increasingly small feature size and increasing complexity. Over the last 10 to 15 years, we've seen a lot of big improvements in the technology and the ease of use of TEM and STEM instruments. And in particular, some key trends are big increase in ease of use, software, automation, overall stability, and the ease of alignment, and improved resolution, especially at low KB. And this, of course, is very much enhanced by the use of aberration correctors. Also improved camera and detector sensitivity, which helps with low dose imaging, and much higher EDS detector sensitivity. So we get better throughput, better detection of trace elements, light elements, and it's also very powerful for 3D EDS and EDS of beam sensitive materials. So STEM for failure analysis. So what do we mean by failure analysis? Well, there are many different kinds of failure, as we've heard already, and I think the contribution of STEM can be in, for example, identifying small particles, causing shorts or open circuits, poor layer coverage, problems with etching, the presence of voids, contamination or diffusion, misalignment of process steps, also problems with ion implantation, or problems with incorrect strain in the material affecting transport properties. And there are lots of other examples, and we may need to compare good and bad structures. We may need to measure things accurately, including very thin layers. We may need to identify foreign substances or missing layers. And in all of these cases, STEM and TEM are very helpful. So the main topics I'm hoping to cover today are, first of all, imaging, STEM and TEM, about EDS in 2D and 3D, dopant mapping, Eels, we heard a bit about Eels, talk about beam damage, which is often limiting the quality of data we can acquire, and also low KB imaging, which is connected, and a bit about metrology and strain measurement, and finally introduce some key technology of our Spectra STEM platform. And I try to do this in the context of semiconductor device characterization and failure analysis. So I'm part of the electron microscopy team. The main product groups that that I'm involved in with are XPS, SEM, dual beam, which David was talking about, and TEM, and I'm in particular going to focus on TEM today. So our TEM system lineup for material science and semiconductor applications is mainly these three, which is the Talos series, which is really high throughput general use system, Metrology AX, which is very much focused on high throughput metrology and automation, and our main high resolution system, the Spectra series, which has Spectra 200 and 300. For this, we can put aberration correctors. So to start just with imaging. So taking really high quality, high contrast, high resolution images is really the most basic use case for STEM and TEM, and is used for a wide variety of materials, including semiconductor devices. And you can see a range of examples for nice images acquired with STEM and TEM here. And some challenges for imaging include getting sufficient contrast. So can you see the feature clearly and sharply? Accurate and precise measurement. So is this shape or size normal or not? Do we get sufficient resolution? And was the sample preparation appropriate? So are we looking at the right location? Is the thickness appropriate? And is the sample in the correct orientation? STEM technology has really taken off and is now very powerful. I think detection has improved a lot. We see here two examples from the same structure. The left is a bright field STEM image. This gives you very similar information now to what you get from bright field TEM. And the right is high angle annular dark field STEM. This gives you a lot of chemical information. So the bright areas contain more heavy elements. And just by varying the detected geometry and camera length, we can really get a wide variety of different kinds of information just from STEM images. Resolution is important, of course. And here we just are comparing an uncorrected image taken on the Talos on the left. So they're both from silicon, and with the Spectra with the CS corrector on the right. So you get a significant improvement in the spatial resolution, which may be very important, or it may not matter depending on the application. And I would say, in particular at low kV, which is kind of a trend at the moment, and I think it often is very valuable. You can see at 80 kV, for example, a big change in the spatial resolution for the uncorrected system is around 3 angstrom, and with a corrector we get less than 1 angstrom resolution. So really makes a big difference to the resolution, especially at low kV. So we have a new STEM detector we call Panther, which was released last year. This, as well as optimizing the geometry, the biggest change most people will notice, I think, is much lower noise, as well as a high gain. So this means it gives you much higher signal to noise ratio in the images, and is very suitable for low dose and high frame rate STEM imaging. So here's a comparison of, on the right here, the previous generation of STEM detectors. On the left is Panther, both acquired with a very low STEM probe current, 1.3 picoamps. You can see a very noisy image on the right, but with Panther, even under the same scanning conditions, we can get much higher signal to noise ratio. And that really helps with overall STEM image quality, low dose acquisition, high speed acquisition. It makes the alignments and also the OptiSTEM auto tuning software much more reliable. So a lot of benefits from using more sensitive detectors. So our next topic is DCFI, which is another new technology for STEM, which was quite widely used in SEM before it became widely adopted recently in STEM also. So this is drift corrected frame integration. So you, instead of taking one slow scan, you take multiple fast scans like this, and then you drift correct and sum the frames together in such a way that you get a single very high quality and high contrast image, which is the DCFI STEM image. It also works for TEM, and much lower scan noise, less distortions, less drift and charging effects. So quite an effective way at a range of different magnifications to really improve your STEM image quality and get more useful information out of each image. So the DCFI feature is actually built into our VLOX software user interface. It's the same software UI for both Talos and Spectra. You can see the DCFI is one of the nice features. Others include easy workflow, a nice EDS frame removal feature that I'll talk about later, really much improved EDS drift correction, which is very helpful, especially at high magnifications, simultaneous Eels EDS, EDS tomography, and DPC multi-segment detection. So a lot of new features as well as ease of use that comes with the software. I think software is really an important trend in microscopy recently. So this is about OptiStem. This is another important software package that we have on our STEM instruments. So it automatically tunes the STEM probe. So you can go from out of focus and astigmatic image to a sharp in focus image just by a single button click. So even users who do not have much experience can get really high quality results on a range of samples without needing a long training process. And this works at medium magnification and also right up to the resolution limit of the microscope. So for lattice imaging, it's still using your sample. So you can just run it just before your final image. It uses contrast within the image itself, and you can correct also the threefold astigmatism and coma. So all of the low order aberrations easily and accurately corrected in a short time using OptiStem. And these are a couple of examples of STEM images. The left one is a bright field image showing a hafnium oxide, silicon oxide, silicon sample, and you can see clear contrast in particular because the atomic columns of the silicon are so clear, and on the right, a germanium silicon interface. So next I'll move on to talk about EDS, which is for chemical mapping. And our main EDS detector, we have a variety of EDS detectors that are available. The main ones are the Super X and Dual X. The Super X detector consists of 4 round EDS detectors, and a particular strength of Super X is the very low background and system peaks. So it gives you very high spectrum quality. And Dual X has a much larger solid angle, so it gives you the highest speed and throughput. But both of them are symmetric design, so they're suitable for effective results quantification and also for 3D EDS data acquisition. So here are some EDS mapping examples. So the left one is just showing, this is in real time, an EDX map from a device sample, and you can see even just in a few seconds that you can see the basic element distribution within the sample. So you can really take a large field of view image, work out what's going on and decide where your features of interest are. And it's also helpful to use the EDX data to locate defects in different regions. So this is just a map taken in just 30 seconds. And the center one is ONO structure, NAND flash, and taken with a lot of pixels. So 4,000 by 4,000 pixels. When you have a lot of pixels, you can really see a lot of detail. And we have another method also to use our maps software to take multiple frames and then stitch them together to form a large field of view that gives you a really clear overview while still maintaining a good spatial resolution. That's very helpful for locating problems and getting a lot of good statistics from your sample. On the right, also a device EDS map. This is showing the effectiveness of the latest software for deconvolution and quantification. So these plugs are tungsten, and the substrate is silicon, of course, and silicon K and tungsten L actually overlap, but we can use effective deconvolution now to see where the silicon is and where the tungsten is and not have them interfere. So you don't see tungsten in the silicon map, for example. Here's another EDS map of a device. You can see a variety of different elements. This one's taken with a relatively high probe current, 3 nanoamps, and in 7 minutes. So you can really get high quality data from a range of different samples, including, a range of different elements, including here we're looking at phosphorus and arsenic, which are dopants, so in relatively low concentration. Of course, we can also do atomic resolution EDS. So this data is from dysprosium scandium oxide and acquired on spectra. So this data set shown here is taken with the Super X detector. You can see the dysprosium and scandium clearly, and in fact, you can determine the slightly more vertical and horizontal dumbbells within the structure. If we acquire the same data set under the same conditions using dual X, we get a higher signal to noise ratio, and we can start to see the oxygen positions more clearly. And we can actually determine the position of the oxygen octahedra by looking at this kind of data. So 3D information in TEM and STEM is acquired by using tomography, which means we take a series of images or maps at different tilt angles, usually from like -70 to +70 degrees. So we really tilt the sample a lot. And if we have a symmetric and high sensitivity EDS detector, we can do the same thing with EDS. So we acquire an EDS map at each tilt angle, and then we can reconstruct to form this kind of 3D elemental map. So here's an example from a 32 nanometer semiconductor device. So we're acquiring an elemental map at each tilt angle and then reconstructing to form a 3D data set showing the position in 3 dimensions of each of the elements. And we can see clearly the element positions, including hafnium, which is a less than 2 nanometer hafnium oxide layer. And this is also a powerful way of identifying defects and other structural problems within the device. So this data was taken with 1.5 nanoamps of current, about 8 minutes acquisition time per map, and a 5-degree tilt step, which means about 4 hours of total acquisition here using the Super X EDX detector. So in the case that the sample is relatively resistant to electron beam damage, we can often achieve very high EDS throughput, and the keys are to have a high EDS detector sensitivity and a low dead time. So a detector that can measure a lot of counts without the dead time increasing a lot. Optimizing the voltage, often using low voltage, is very helpful for improving or increasing the EDS count rate, and being able to generate high probe current at your desired spatial resolution, even at low kV. So with this combination, we can often achieve get really a lot of EDS counts and a lot of EDS data in a short time, even looking over a wide area. Now here's an example of dopant mapping. So we're looking at here on a 40 nanometer NMOS device at an arsenic map and a phosphorus map. And you can see the distributions clearly. And we've plotted here line profiles in 2 locations to show what the sensitivity is. And if we look here, you can see the noise level is around about 0.1 atomic percent. So we can detect, so that's about the sensitivity limit. So if there's more than 0.1 atomic percent, then we're able to visualize the distribution within the EDX map. So boron is more challenging because not only low concentration, but low X-ray yield. So you can see, this is one of the better efforts I've seen. You can see boron concentration increase near the surface. So it is possible to visualize the boron, but the signal is relatively low. So boron is quite challenging to look at dopant concentrations. And here we're using 80 kV to try and enhance the signal. So for boron, Eels gives you much better signal for boron, but in the case of doping in silicon, it's quite challenging because of proximity to the silicon edge at 99 eV. So the background fitting for the Eels data is also quite difficult in Eels, I think. An alternative approach is to actually visualize the electric fields that are generated at a PN junction, and we can do this using DPC STEM. So DPC uses instead of a round detector, a 4-segment detector. So these are 4 different detectors, and with 4 detectors we can measure the shift of the stem disk, which is caused by passing through electric fields within the sample. So this allows us to measure the electric field, and also by integration to measure the inner potential in the sample. So here's an example of visualizing a PN junction of a silicon carbide power device. So this is the structure. So there's a N+ diffusion layer, so PN junction, but in normal dark field stem image, you cannot see it. But by using DPC, we can see that the PN junction here, you can see the white line. This is the PN junction, which is visible in the B-D. So this is the vertical electric field measurement. And if I integrate this forms an IDPC image, you can see this black region here corresponds to the diffusion layer. So it's possible to visualize the diffusion layer and see PN structures using this DPC stem technique. Although so far we think you need quite high concentration of dopant in order to be able to see it clearly. Next, eels. So we heard a bit about eels already. That was which is very nice. And I'm just showing some data here to demonstrate that yes, the main alternative to EDS for element mapping is of course eels, and you can of course get very similar results. So you get very high quality and clear eels maps are in many cases possible, such as these images from a FinFET and this from a metallization layer cross section. And there was a question, I think, earlier about comparing EDS and Eels. So I've actually made just a table to try and sort of summarize some of the advantages and disadvantages of EDS and Eels. So first, for EDS, so recently, so the last 10, 15 years, very large, fast detectors have become available, and the sensitivity has improved dramatically. So that whereas light element mapping didn't used to be possible, now it's really becoming quite practical to take EDS maps of even oxygen and nitrogen and other light elements. EDS is simple to operate, easy to learn. You can acquire all the elements simultaneously, so it's very easy. Almost any sample thickness is okay, suitable for quantification, very suitable for recursive mapping, which is taking multiple frames and summing them together. This is very helpful for drift correction, especially at high magnification. It also works well for 3D imaging and is relatively low cost. But still, the sensitivity for light elements is definitely lower than for the rest of the periodic table. On the other hand, Eels, which is also very powerful for mapping element distributions, as we've seen, this does often have better sensitivity for light elements. So that's often a big reason for using Eels. And it provides independent information. So if you're looking at something really important, being able to get the same information independently from Eels and EDS is, I think, often very powerful as a double check. And of course, as we saw, oxidation state mapping is possible with Eels, and that kind of information is just not present in an EDS map. But on the negative side, it is more complex to operate, requires more experience, typically different optimal acquisition settings for different elements. So it takes more time, it requires a thinner sample, not very easy to quantify. In the case that edges for different elements are close together, it's quite hard to do the background fitting. So you can get artifacts in your maps, not very suited to recursive mapping and quite a lot more expensive. So, both are valuable. It's nice to have both. And I just tried to summarize there some of the pros and cons of EDS and EDS. The next topic is beam damage and low KV imaging. So beam damage is often the limiting factor for EDS data quality and detectability. So the reason is that EDS requires a lot higher dose than just imaging in STEM or TEM. Damage mechanisms vary with material, and they include knock-on damage, which is usually worse at high voltage, and heating or radiolysis. This is sort of bond breaking damage, which is normally worse at low voltage. So you can see, but an important factor is that EDS count rate almost always increases at lower voltage. So if we look here, this graph on the right, I'm comparing the count rate generated with the same current as you vary the acceleration voltage. So here, as I move at the same 2.5 nanoamps current from 300 kV to 60 kV electrons, you see almost a 3 times increase in the EDS count rate. So you get much more EDS signal in your map using the same current. Okay, so this is always a factor that's worth considering. And I think it's a really big reason for using low voltage to acquire STEM data. Okay, so optimizing the voltage is going to be a really important factor in getting the best data on your sample. So here's an example showing beam damage. So this is actually an Eels map. So the upper maps are taken in 2 minutes, the left showing silicon and the right hafnium. This shows more or less the original distribution. After mapping for 6 minutes, though, you can see, although the silicon distribution didn't change much, the hafnium is really starting to spread out. So the hafnium, because of beam damage, is diffusing or spreading out or being knocked into adjacent layers, and this is no longer the original structure. So you need to be careful. This kind of beam damage is what we need to avoid when we choose our mapping conditions and the length of time that we can map for. So a useful feature in the software now is a frame removal. So with frame removal, what happens is we acquire EDS, well, time-dependent EDS, and at a certain point, you can decide later that damage has occurred and you only use the, for example, if damage occurred after 3 minutes, then you can discard all data after 3 minutes and just select the frames up to 3 minutes to form your final map. This means you can always get the optimal map instead of having to consider what the optimal time would be before you acquire the data. So very helpful for always optimizing your EDS map data from beam sensitive samples. So here's an example on an ONO structure. So in this case, we acquired 130 EDS frames, and then looking at the data, judged that the best balance between the signal to noise ratio to be able to measure effectively and avoiding radiation damage was taken at around 70 frames. So this was the optimal data. So for high resolution, so until not so long ago, this was really the common sense that even with a CS corrector or an aberration corrector, you could get sub-angstrom resolution easily at 200 kV or 300 kV. But if you move to 60 kV, you might get 2 angstrom resolution, and 30 kV might give you 3 angstrom resolution. So you can sort of see a bit, but it's really not very nice to use. Now, this is no longer the case. So with the latest generation of aberration correctors for STEM, on Spectra, we use the S-Core now. It's really a new design that allows you to correct even up to 5th order aberrations. So this A5 aberration, this is 6-fold astigmatism, can now be corrected for each acceleration voltage. And that's really powerful, especially for improving the achievable resolution at low voltage. So here we're looking at 60 kV, so pretty low voltage, high resolution STEM of gallium nitride. And you can see the on the right here, both the gallium and nitrogen positions are clearly visible, and with resolution in this case about 75 picometers visible at 60 kV. So that's a really high resolution that's now achievable, and a big part of that is use of the S-Core corrector. And here are a few example images taken at 60 kV, which I think is almost can be used as a standard voltage setting for acquiring images. The left and right are both STEM, and the central image is actually a 60 kV TEM image. And even at 30 kV, we can now get atomic resolution imaging. So in this case, the chromatic aberration also becomes important. So combination with either our XC-FEG, cold FEG, or with monochromator is important in order to achieve the guaranteed resolution at 30 kV, which is now 125 picometers. So just a little over 1 angstrom. So I would like to move to talk about metrology, so measuring features and also measuring strain. So all of our STEM and TEM tools now have pretty good accurate measurement capability, but in particular we have focused on the Metrios AX as a system where we really try to optimize both the ease of use and the optimization and also the accuracy of measurement. So we're able on this system to automatically find lamellas, even multiple lamellas in an automated way, just the zone axis, find the feature and do automated measurements in a way that's much more repeatable than doing them manually by different users. So this is a system that's really focused on accurate measurement and metrology. Strain can also be measured effectively. Strain, of course, in devices is often very important. It affects the, for example, in transistors, the switching voltage, the speed and the amount of power and heat generated. And we can measure strain by measuring the lattice parameter, which is the information that can be measured very accurately in the diffraction pattern. So we use nanobeam diffraction mode, focus a small probe on the area of interest, and then we can scan it and measure how these lattice parameters change, and from that get strain maps. And here's a two-dimensional map showing strain distribution in a transistor. And if we scan here from the substrate into the transistor region, we can take a line scan and measure how the strain varies. You can see the strain increasing in this orientation as you move into the transistor region. I'd just like to finish talking about some key technologies of the Spectra series. So Spectra has two main gun options, the XFEG monochromator and the our new cold FEG gun, the XCFEG. So the XCFEG is a really high brightness cold FEG, also has a low energy spread. So I think it's going to be powerful, not just for imaging, but also for a wide range of Eels applications, and has a lot of benefits for ease of use. You can see in this graph here a variation of probe current with the energy resolution using the XCFEG gun. And you can see even with very high probe current, more than 500 picoamps, the energy resolution stays well below 0.4 eV. And we can reduce to 0.3 eV energy resolution and still get 200 picoamps. That's enough current for a lot of most Eels and EDS applications, even with probe size of 70 picometers. And even at 0.26 EV energy resolution, still 50 picoamps of current. So you really enough current, even at these good energy resolution regimes, to get a lot of really valuable data, even at atomic resolution. When you need the ultimate energy spread, you can use the XFEG monochromator gun option instead. So a very popular key feature of Spectra, and indeed all of the Titan series, is the constant power lens design. So it means even as you change the strength of all of the lenses in the column, there's no change in the heat generated. So you don't see any thermal drift as you change magnification, go to low mag, change between TEM and STEM, and even normalize all of the lenses. No thermal drift, so almost no waiting time when you change modes. That's really a big advantage of the Spectra system. We've also redesigned the base, so we have much improved active and passive anti-vibration systems, and optimized cabling to reduce vibrations from the floor passing to the column. So these are, not very exciting to talk about, but actually make a big difference. And they're one of the main reasons we've been able to guarantee 50 picometers resolution on Spectra for the first time. So that's pretty much all I wanted to say. Just one extra thing. So actually we have some quite exciting new technology that's being announced tomorrow. This is related to Spectra, and in particular improvements to the high tension switching. So switching of the acceleration voltage, which becomes much faster, and a big improvement in EDS performance. So there's going to be a webinar to launch that. Actually, there's a sort of material science one is tomorrow, and the semiconductor one is the day after. So if you're interested, I definitely recommend it. Guest speaker is Nestor Zaluzek from Argonne National Laboratory, who's been doing a lot of the testing. And you can find it looking up Zaluzek webinar, or just screen capture this, or send me an email, and I'll be happy to share the link with you. So thank you very much for listening. I mainly talked about STEM and TEM imaging, EDS mapping, dopant profiling, Eels, beam damage, low KV, metrology and strain measurement, and some key technologies of spectra. Thank you very much.
All right, thank you, Dr. Alex. So very interesting updates on quite several up-to-date information on analytical equipment. So before I pass you a few questions related to your presentation, I would like to respond to one question by Noor Ahmad, whether we must have TEM spectra equipment in Kuala Lumpur, which Dr. Alex has been saying just now. The answer is no and yes. No, not currently, but yes, we have the intention to purchase, and we are planning to get it available by again end of 2022. So keep in touch with us. We will update you on the availability. The second question that I would like to respond here is regarding the use of 3D X-ray to detect metallic foreign material inside IC packages. Our experience didn't result in a satisfactory result when we used 3D X-ray to detect metallic foreign material. I don't know whether Dr. Alex have any experience outside the use of X-ray and also probably CSAM. So maybe if you have any idea, you can also respond to that question. So the question for you is from Muhammad Nizam: how to increase count rate if we have a beam sensitive element? I mean, if you use TEM EDDS, how do we play with the count rate for a beam sensitive element specimen?
Right. Yeah. So of course it's difficult, and I think you can try changing the balance between the current and the acquisition time. That actually sometimes makes a significant difference. So you try to do a longer mapping with a lower current. That can work. Of course, the biggest difference probably comes from the sensitivity of the EDS detector you're using. But once you have a microscope, you can't change that. And I do recommend you to optimize the acceleration voltage to try and find the voltage at which the damage is lowest, but you get the highest count rate. That's going to be different for every material. So it's really worth trying to find out what acceleration voltage gives you the best results on your type of samples and application.
All right. Okay. This question is probably from your potential customer. It was about the preparation for site. If someone were to install, as you know that TEM, they have this tower, and as I mean, the preparation for the site will be quite extensive, and if not expensive. What would be the site preparation required for installing TEM equipment, for example?
Right, so the site definitely makes a big difference. We've tried with the enclosure and the anti-vibration system to reduce the site impact as much as possible. But of course, it always helps to reduce vibrations. You want a really stable floor. You need air conditioning system that really keeps the pressure and temperature constant. That's very important, and you need to avoid electromagnetic interference as much as possible, both DC and AC. If you can do that, then it makes our lives much easier when installing the microscope, and I think in most cases you'll get better results.
So it is not advisable to have it in a multi-story environment, for example, as third floor of a building.
I think systems are more stable than they used to be. in a variety of environments. On the other hand, the requirements or people's expectations about the stability have also increased. So technologies such as DCFI are very helpful. You can do a fast scan and sum the images, and then even if the site is not great, actually often you can get very nice looking images. So this kind of technology is very helpful to allow you to get really quite nice data, even when the site environment is not great. So even in non-ideal sites, in many cases we can still get good data. That's true. But at the same time, trying to get the best site you can, it really does make a big difference to the quality of data and the ease of use.
Okay, I think we are running out of time, and I think that's the question related to your presentation. So we still have a few more questions that still are unanswered, and we will follow up with all the questions. Hopefully, as I mentioned just now, please drop by your contacts so we can follow up with you on your questions. So I guess thank you, Dr. Alex again, and over to you again, Lawrence.
Thank you.
Okay, thank you, Dr. Alex, and also thank you to Dr. David earlier on who made his presentation. Okay, seeing that this webinar attracted quite a large interest among scientific and engineering community of advanced failure analysis technology, we initiated a Facebook page for failure analysis technology in Malaysia. It can be accessed at My FA Tech. This community page will be a great place to continue our discourse on failure analysis topics. The recording of this webinar, as well as some of the questions in this webinar, will be posted at the FB page for us to have continuous interactions on those scientific and engineering focused areas. We hope through this FB page, we can continue to learn from each other on relevant and latest failure analysis related happenings. We have also invited each and every one of you to share and forward relevant news, articles, or technical sharing for mutual learning among us. We have a plan to conduct a quarterly webinar like technical sharing related to more interesting dimensions of failure analysis, technologies, and methods. We'll post this once we have details on the technical sharing. Our goal is to be able to promote greater understanding and learning of failure analysis technology and method in Malaysia through this FB community page. I certainly hope you'll access and be involved in the My FA Tech FB page. So ladies and gentlemen, the address is right here. Take a quick look and you can share it with your friends so that all of us will be able to share and be a part of this community. So with that, ladies and gentlemen, I'd like to thank our speakers, Dr. Shohari, Siti, Dr. Alex, and Dr. David for their knowledge. And I'd like to thank each and every one of you for attending this webinar and supporting our My FA Tech Facebook page. So can we get a web photo with all our presenters? Presenters, please switch on your camera. Okay, with that, ladies and gentlemen, thank you very much for joining us. And till we meet again, stay safe and goodbye. And big thank you to all the organizers, Mimos and Crest, and also to all those working behind the scenes, our secretary. A warm thank you to each and every one of you. Thank you, ladies and gentlemen. Till we meet again. Bye-bye.
Thank you. Bye-bye.
Thank you.